I'm going to record our lesson, and our first topic today is the collection of data. So in the past classes, we've talked about data in general, and we've talked about visualizing data. Today we're going to talk first about how we actually get all of the data that we are visualizing and processing. So where does all this data come from? As we are discussing processing and visualizing all the data that we're talking about, it's important to know where the data is actually being sourced from. There's a couple of questions we need to answer. Question one, how can computers help us collect data? Question two, how can we best collect and store data so that it is able to be analyzed by computers? So what can we do in our collection process to make it easier for us to analyze later down the line? So, answer to question one, how we actually collect data. There are lots of different ways that we can collect data. Here's a few examples. We can use surveys. So if we want to get information from people about people, we can send out surveys, or we can have a link to a survey posted somewhere, and we can have people respond to this survey. Keep in mind that not everyone wants to take surveys. They take time out of your day. So it's possible that we could get skewed results, and results where only people who want to respond to a survey would respond. So just keep that in mind while you're working with surveys, but surveys can be a great way to gain a lot of information about people. We can use sensors to gain all kinds of information about the world around us, or even about ourselves. We can use thermometers, we can use barometers to see what the weather's going to be like. There's lots of different types of sensors that we can use to gain information. And usually these will interface directly with our computers, which lets us store the data that we are collecting directly. We don't have to go through any other means to store our data because it's already going to be going straight from the sensor to the computer, which is very convenient. Another kind of data that we can capture is transactional data from credit cards. Anytime you make a purchase with a credit card, that's going to be tracked by the company that owns the credit card. So this allows us to look back and see our own spending history. It also allows credit card companies to see how we are spending our money, and then maybe use that information to shape how advertising gets sent to us. So just keep in mind, anytime we use a card, it gets tracked. Similarly, anytime you visit a website, you're likely having information collected about your visit. It might not be personalized data, it might be anonymous. They might just be tracking where you're clicking, the time you're spending on different pages, which browser you're using. But lots of websites will use this kind of information to see how their users are using their website. And this allows the website and the people running the website to tailor their website to people who visit it. Can make their they can specialize their website to be however people are actually making use of it. In our last form, there's many more than these, but our last example is crowdsourcing data. If you, let's say this is going to be very similar to a survey, except we're just going to pose a single question to, let's say, a whole bunch of internet users. We could send out a poll on Twitter and say, just answer this one question. And we can get a whole bunch of different people to answer this question. We can also find or track the behavior of a large group of people. If we see lots of people are tweeting about a specific event in a specific location, we can be pretty sure if some kind of event is happening in that place. So that people are talking about an earthquake in Venezuela. There was probably recently an earthquake in Venezuela. We can keep track of things like that just by seeing how people are interacting on the internet. So once we have actually done this data collection, where do we put it? Where do we store it? The first place we're going to store it is on our computer's local disk memory. So just local to your computer so that it's accessible directly. After that, yeah, you can upload your information to a database, which is a computing system designed very specifically for storing large amounts of information. And if the data is sensitive, so if it's login information, if it's medical records, if it's anything we don't want hackers to know, we can encrypt our information when we store it in that database. And that means that even if a hacker does manage to get access, they won't be able to read all of the information because they won't have the decryption key, or at least they shouldn't have the decryption key. Most data is going to be stored in these things called data centers, which are just big warehouse-sized buildings filled with computers that are used to store large quantities of information. They'll look like this. They'll have server racks that are just full of computers designed to store all kinds of information. And lots of different online companies are going to have their own data centers, like Google, Facebook, Amazon will all have warehouses full of computers for storing data. Now, as you could probably expect, accessing all of this data in an easy and efficient way can be somewhat challenging. So we need to develop, fortunately, they have developed ways for us to interface with these database systems. And there are programming languages called database query languages, like SQL, or the structured query language. That's the most common type of query language for interfacing with databases, though there are others. So languages like that and data APIs, application programming interfaces, like we've learned about in the past, these allow us to ask databases for the data we want when we're using our programs. So someone who owns data, so let's say YouTube or Google, they might give us access to an API where we can call different functions and gain access to the information those functions provide. Those will hit the database, will access information, and send it to us through that API. And we can write in SQL, or we can have our programs create an SQL query that will be sent to a database to retrieve whatever information we might be looking for. Now, keep in mind, while we're working with data, some kinds of data are much easier for both us and computers to process and to visualize than others. So if we're working with numbers, that is almost always going to be easier to process than text is. So if we can somehow make our data be numbers, or we can turn it into numbers, correlate it with numbers, that's going to make it way easier to process. Also important is making sure that the data we're working with is sanitized. And this means that we have to sometimes throw away data when it's not formatted correctly. So let's say I gave a survey where I asked the user to enter their age in a text box. I didn't use a drop down, I used a text box. And someone entered $, instead of an actual number. Since I'm not able to visualize $, and additionally, it's not going to fit with the rest of our numeric data, I can't really put that on a chart anywhere, I'm going to discard that entry. I'm going to get rid of it, I'm going to ignore it, pretend it doesn't exist, because otherwise my data set is going to be harder to work with. So we are sanitizing our data set to make it easier for us to actually work with. Now, keeping track of the method we're using to collect data can also be a big factor. So let's say we want to do a survey of all of the people in our class. We could either have everyone write their answers on a piece of paper, or we could have them enter their answers into a spreadsheet. Which of these would make it easier to process down the line?
Spreadsheet?
Spreadsheet, because if we are going to be processing this data, we'll probably have to put it in a spreadsheet anyway. So if we can get rid of the step where we have to read all this pieces of paper and put it in a spreadsheet ourselves, that can save us a lot of time. If all the answers are directly in the spreadsheet already, we've saved a whole bunch of time doing that. On a similar vein, let's say we want to find the eye color of every person in your class. Here's a few options we could use. We can have everyone give you a physical picture of their eyes. We can have everyone send you a digital picture of their eyes. We can have everyone fill in a survey where they write in the color of their eyes, where they type it in. Or you can have everyone fill a survey where the colors can be chosen from a drop-down menu. As you can see, we're getting easier and easier to process, or less and less work on our end in the processing, because if we have everyone give us a physical picture of their eyes, we have to look through all these physical pictures. We have to see what color we think those eyes are and then mark it in a spreadsheet. And do the same over and over again. And it's not much better with a digital picture, because then we have, we're doing the same process. We're looking at all the different pictures and trying to figure out what color those are. If we have people fill in a survey where they just type in their number or their answer, this is definitely better than having us do it ourselves, having to try and figure it out. But we open up the door for people to potentially put in bad things. They could put in orange. They could put in I don't know, glass. It doesn't, like, they could put in whatever they want. It doesn't have to be an eye color here. So if we actually make a drop down with all of the possible values, then we are making sure that our data is going to be as usable as possible, because all of our values that we get from our classmates are going to be valid inputs. And it makes it easiest for us to do processing afterwards. We don't have to do any data sanitization. And we'll also already have it in a digital format. Very convenient. So the moral of this story is that computers can help us automate data collection, which makes it easier for us than ever to gain all kinds of information about the world around us. Storing and accessing this data can be challenging, although lots of technologies have been developed and put in place to help alleviate this challenge. You can use databases, you can use database query languages, all these kinds of things. And like we've been talking about, there is so much data being collected and stored every single second. There's data being collected all the time. All right, topic 2 of today is talking about data limitations. So, last class we talked about data visualizations. And if you remember, I showed you a pie chart where it was absolutely illegible. All of the slices were white. They're all spread apart. It was not easy to understand what that pie chart meant. So it's possible for our visualizations to be misleading or give us even false information. So while visualizations can make reading and interpreting our data easier, there are still limitations to what we can conclude from looking at them, especially if someone creates a visualization in a way that's purposefully misleading by skewing the axes, messing with labels, or just leaving out relevant data points. So we're going to look at a few different types of misleading visualizations. Our first kind is truncation. So one way we can make our data misleading is by truncating the axes. If we look here, we have the same data, but we have different y-axis. On the left, our smallest value on the y-axis is 3.140, and the largest is 3.154. We have a very, very minor difference between those values. So it looks like the interest rates are skyrocketing across the years, where if we have our y-axis start at 0 and go up to 3.5, it looks like there's literally no change happening here across our 4 years. That's 5 years. I can count. So having a slightly different scale increases or it can change how we see this data drastically. Now, it's possible that we might want somewhat more of a middle ground here. We might not necessarily want to start at 0. We might want to zoom in a little bit, but having the scale here be this small makes any change look incredibly drastic. So this is just one way we could make it misleading. Here's another example of that. We have this pitcher in baseball, and across 2 different years, his pitch speed went from 77.3 miles per hour to 75.3 miles per hour. The difference there is just 2 miles an hour. Not a huge amount, but the bar on the left looks twice as tall as the bar on the right. It looks like there's been this huge, huge change in between those 2 years, when in reality, it's a very small fraction. It's only 2 miles per hour. So the change is not actually as drastic as those bars might lead you to believe. Another way we can mislead people with our visualizations is by just omitting data. If we look at these 2 graphs, they are plotting the same thing. We see all these data points on the left graph. We can see it going up and down, where on the right, it looks like all the values are pretty much only increasing. There's a very small dip here, but if we compare, we can see we're getting rid of all of the years, all of the odd years in our left graph to make that right graph. So we're getting rid of 2001, 2003, 2005, 2007, and 2009, which is going to make our graph look a lot better. It's going to look like it's increasing over time rather than having all this fluctuation. So if we just kind of fuzz over that information, if we don't include it, we can once again make it a misleading visualization. We can gain the wrong kind of understanding from this graph. If we break the conventions of how we're expected to see graphs, we can once again trick people into thinking that data says something it doesn't. If we think about pie charts, the angles, all the values should add up to 100%. But if we look at this chart, it looks like the city is contributing 50% of the funds. If we do a little bit of math, though, the city is contributing 265 million. Unknown is contributing 10 million. Maloofs is contributing 85 million, and AEG is contributing 50 million. Now, all of those slices look roughly the same size, even though they are wildly different in number. And if we add those up, that does not add up to 265. So if we look at what the actual chart should look like, here's what our actual pie chart would look like if we used the correct slice sizes. So our city contribution would be much, much larger than just the 50%. Our unknown contribution is going to be much, much smaller than on our original graph. So making sure that we are following the conventions of how our graphs are meant to be used can make sure that our data that we're presenting isn't misleading, like it would be, like it is in this picture here. All right, and another misleading thing we can do is say that correlation and causation are the same thing. Correlation is when 2 data points are, they follow a similar trend. So if we look at these 2 lines, they are roughly the same shape. They're pretty well correlated. But if we look at what these lines represent, it's letters in the winning word of the Scripps National Spelling Bee and number of people killed by venomous spiders. I don't think that those 2 things have anything to do with each other. So even though their data points are pretty closely correlated, one of these did not cause the other to happen. These two data points are completely separate from each other, even though their graphs line up pretty closely. So there's a whole website of these silly correlations where it ties all of them together. You can even, they have a tool where you can find your own correlations. You can find two different data points and it'll graph them together and say, hey, this correlates with this at this correlation rate. So how closely do those lines match? Even though obviously none of the things that we're looking at are going to be causing the other. So just remember, anytime you're working with two data sets, remember the difference between correlation and causation. Another important factor when we're working with data is the data about the data. Information about how this data was collected, who collected it. There's all kinds of things we need to know if we're going to make sure that the data we're looking at is valid and worthy of being studied. So all this information is called the metadata for the information we're looking at. Just like last unit, metadata is referring to information about information. So we want to examine the metadata for any kind of data we're studying to see if there might be bias in the data that we're analyzing. So we need to ask, where did we collect this data? Is it possible that we only surveyed a specific group of people? Who collected this data? They might have a bias in who in what kind of data they wanted to collect. When was this data collected? If it's really old, it might not be relevant or pertinent anymore. And how large is this data set? If we have a very small data set, it's less likely to be indicative of the world at large. The larger our data set, the more likely it is to be related to our actual world and how it works. So we want to make sure that we have large, complete data sets that are accurate to the way that the world actually works. And some questions just cannot be answered if we don't have the correct data. For example, we can't plot annual trends if we only have data from 1 year, because you can't make a line with only one point. You can't determine worldwide opinions if you only interview Americans. They're only going to have an American perspective. So making sure that we're aware of the limitations of our data is important because we want to make sure we're doing valid and meaningful analysis with the data that we've collected. We don't want to do bogus analysis or produce potentially misleading results by showing information that might not be 100% accurate. All right. All that makes sense? Cool.